Hi everyone. In the previous lecture, we discussed about how to compute carrier to interference ratio in the presence of a single interferer. Though it's not a perfect analysis, it's not a perfect approximation to make, we got an idea about what does carrier to interference ratio depend upon. We showed that a CIR is proportional to square root of 3n. Okay, and again there was a power of path loss exponent as well. So it showed us that we could increase the path loss exponent or we could increase the cluster size. Both of them would give us a good carrier to interference ratio. But increasing the cluster size will lead to a smaller number of smaller number of clusters. So M reduces, which means the user capacity reduces. So that is something we studied. Now the problem is the goal of the whole analysis, the McDonald's work was, he said we'll go for frequency reuse. So using frequency reuse, we have to deal with interference. So which means it's very important to compute how to estimate interference. Okay, that's the whole goal of this exercise that we are doing right now. So having an accurate, what we discussed in the last class was just a very brief introduction to carrier to interference ratio. So in this class we'll see how to estimate carrier to interference ratio more accurately. Okay, we also discussed what is interference limited systems and noise limited systems. NL is noise limited, IL is interference limited systems. Okay, and we discussed if your path loss exponent n is really high, then your carrier to interference ratio CIR will be high because it's proportional to nth power of the cluster size. Okay, so if you're going to have a higher path loss exponent, of course you are going to gain in carrier to interference ratio, but unfortunately your signal, the received power that you're going to your mobile phone is going to receive will be decaying significantly, will be reduced significantly. So normally if you recall from the link budget analysis, we said for every receiver has a noise level, a signal level here, and an interference. So interference can be either above this or below this. Okay, if your interference is above the noise level, then we call it as interference limited systems. Okay, or if it is below that, we call it noise limited system. So now the point is that in the presence of a very high path loss exponent, it's not good, it's bad. I mean, if you have very high path loss exponent, both the signal and interference will reduce. So signal will reduce and interference will also reduce. It might happen that your interference power has gone down significantly, but your signal power was also reduced. So Pi has come down, but P sig is also signal power also reduced. So now a system might have been interference limited before. Let's say there were two experiments we performed, one with a lower path loss exponent and then one with a higher path loss exponent. Previously the system might have been interference limited, but once we go for higher path loss exponent, it might become noise limited. Okay, so fundamentally you have to satisfy both CIR and CNR for your system to work. Okay, both have to be satisfied for you to get the desired BER, bit error rate. So now since in a cellular system, especially a cellular system where there is no line of sight path, we'll also have to deal with interference. Okay, in addition to the noise, there will also be interference, not because of line of sight path, but that's because of frequency reuse. We are reusing the frequency again. You can have a line of sight path and still have interference if there is frequency reuse happening. Okay, so the McDonald introduced the idea of frequency reuse to solve the problem of capacity, but that caused a new problem of interference. So the goal is, it's very important to estimate interference very accurately. So in the previous example, we assumed there was only one interference, but that is never the case. So what I have shown here is for a cluster size n equal to 7. I am taking the example of n equal to 7 because that was the first cluster size which was used in the first generation cellular communication systems. So shown here in green here is the mobile station. So let me exaggerate this. So shown here is your mobile station, which is now at the edge of a cell. Okay, and we are picking that because we are doing the interference analysis at the edge, because that is the point where your carrier power will be minimum. Okay, so if you meet your specification there, then we are fine. Because if you, let's say you want to compute interference at the center, it may not be a good suggestion because your carrier power is already very, very high to begin with. In addition to that, your interference is also slightly smaller. Okay, the further you move away from the center, you are going to put yourself in the proximity of other interfering base stations. So these are the base stations. All these base stations are going to use the same carrier frequency to transmit it as this base station is using it here. Okay, so that's the problem. And now our goal is to find out what is the interferer contributions from each of these base stations. What does interferer power depend upon? Your interferer power mainly, I'm going to call it PI. It depends upon the transmit power of the base station, the interfering base station, and the distance of the interfering base station to the mobile station of interest. Okay, the mobile unit of interest. So let Di be the distance from the ith interferer. So then the ith interferer power will depend upon the distance mainly from the mobile station to the interfering base station. So the problem of estimating accurate interference reduces to problem of estimating accurate distances. Of course, path loss exponent is a given. So if I assume that we know the path loss exponent, then it's a function of distance. Okay, and here we are assuming that all the base stations are transmitting with the same transmit power. Now interferers are of different types here. Based on their proximity, we classify them into different kinds of interferers. So the first interferers are the nearest interferers. So those are called the tier 1 interferers, shown here on a circle. So if you follow the rule wherein if I move I equal to 2, this is n equal to 7, so I equal to 2 and j equal to 1 from every cell on all the 6 sides, 2, 1, 2, 1, you will end up meeting the first set of cells where you will be reusing the frequency. So that's the reuse distance, or you will be reusing the frequency. And those shown in red here, these are all tier 1 interferers. So these 6 of these interferers, these guys are all what we call as the tier 1 interferers. Okay, so they are the closest, and therefore they will have the maximum effect on your mobile station. Okay, because we know that the interferer power decays down exponentially. It reduces by d power n. Okay, it's a function of distance. So the farther away the interference will have less effect. The next one is the tier 2 interferers. So now how do you find that? You stand on any one of the tier 1 interferers and apply the same rule, 2 units and 1 unit from here. Okay, so then what you find will be the tier 2 interferers. So these tier 2 interferers will again fall nearly on a circle of a larger radius, and these tier 2 interferers, in fact I have shown only 6 here, it will actually be 12 or even more, 12 mainly. So these are called tier 2 interferers. Okay, so to estimate the actual carrier to interference ratio, you will have to compute the PC, that is the carrier power at the cell edge, divided by sum of all the interferer powers. So this Pi here is actually Pt divided by Di power n. It's there is some constant of proportionality alpha, Pt divided by Di power n. So we know again this comes from we know how to estimate the received power, using the free space path laws and D-break models and so on. So that's what this interferer power will be. Okay, but we know that if you see from this figure, we've already discussed, the tier 1 interferers are the one that's going to matter the most, because if you move farther away from the cell, that as the distance increases, the interferer power goes down exponentially. So it won't, the tier 2 interferers really won't contribute as much as a tier 1 interferer will. But of course, to get a more accurate estimation, you have to include every possible interferer. Okay, so this is a wireless scenario. Maybe you might sometimes have a direct line of sight path from your mobile station to some other interfering base station, and every other base station maybe some obstacle has come in between, and so in those cases, that's for an accurate estimation of powers from all the base station, from all the interferers. So for our analysis, I'm going to ignore the tier 2 interferers, and we'll try to mathematically analyze or come up with an analytical expression which we can use for our computations for tier 1 interferers. So that will be the exercise of this problem here. So why are we doing this? So to again get a very good estimation of carrier to interference ratio, and we know that the carrier to interference ratio is a function of reuse distance, reuse distance ratio, which is d by r. It's a nonlinear function of d by r, and also it's a function of the cluster size. So it gives him an idea, okay, is this cluster size fine? I mean, do I have to live with interference or not? So that's what this analysis tells us. Now it is convenient if I express again, if you recall, the interferer power is only a function of the transmit power of the base station, of the interfering base station, and also the distance from the ith base station, the interfering base station, to the mobile station of interest. Okay, so we need to estimate this distance. Now what are we going to do in this analysis is we are going to express this distance in terms of d and r. Okay, we are going to express this distance in terms of d and r. The reason being that we have already derived an expression for carrier interference because if I write it in terms of d and r, then I can reduce the expression to in terms of the cluster size. So it gives me a simple hand analysis results. I can just to a first order I can analyze what is actually happening in the system. Okay, so again, to get an accurate estimate, you have to rely on the field experiments and very good softwares. So there are very good softwares which can do that job for you, estimating interference. If you feed in the geography information and all that, we have to do on the field experiments and also very rigorous software analysis. So these methods, the analysis that we are doing, it's for a first cut analysis. Okay, so for engineers, we can just come up with a first order analysis to see whether this cluster size is okay or not. Okay, now we have to find the distance from the first tier 1 interferers, 6 tier 1 interferers, to the desired mobile radio station. I have assumed this mobile station is at the cell edge where r is the cell radius. So first we will quickly find the distances which are easier to compute. So for example, I will pick this. So this is the cell radius r, and in all the analysis, in this analysis we are going to assume d, the reuse distance is actually much greater than the cell radius r. If r is the cell radius, now we know the distance from the center of the interfering cell to the desired cell is nothing but d. Okay, and this distance here is r. Okay, so this distance, now we are supposed to find, so this distance from the center to center is actually d. So this is r. Okay, this is the center. Okay, I've shown it in a curved way, but I think you get the picture. So this is r here and this is d here. Now if theta is really small, if theta is really this theta, if d is much greater than r, then of course this theta is going to be really small. This angle is going to be really small. Then I can approximate this angle to be close to 180 degrees, and this distance d, this distance is shown in dotted blue line, will simply be d minus r. So the whole distance minus r. So this, I am approximating this distance to capital D, and then if you subtract r out of it, you get this distance. So you get d minus r for this. Now similarly, we will try to estimate here for this one. So we know from the center to center, this distance is d. Now to find this, what I am going to do is I am just going to project this onto this axis. I am just drawing nearly a 90-degree line and project it onto this axis. Okay, onto this cell. Now this, if this is theta, this distance from here to this, at this point, this is going to be d cos theta. Now if d is much greater than r, okay, so if I assume d to be, see this is your cell radius, if your d is much greater than r, I can assume theta to be very close to 0. Okay, so if theta is close to 0, again you can see here tan theta will be r by d. If I assume d is much greater than r, I can assume theta is close to 0. So then d cos theta will be equal to d itself. So this whole distance can be approximated to d, and we already know this distance. This is one of the side of a hexagon, which will be r. So from this center to this center, the distance is going to be d minus r. Okay, so we get two distances which are d minus r. The next one is this. So from the cell center, we are supposed to find this distance. So this distance is going to be d. Again, I'll do a projection like this. So again, this is theta here. Again, we'll make a similar approximation. If your this is r, so if your I'm going to project this onto this line here, so this will become d itself. If your theta is very small, I'll get d cos theta as the projection. I can approximate d to be very close to theta to be close to 0, so then d cos theta will be d itself. Okay, so again this can be approximated to d. Now next, this is a little easier one. So for example, if this is the center, the same way we did it for d minus r, it will work for d plus r as well. So this center to this distance is d, and this radius is r here. So I am going to assume theta again is very small. So this distance is d and this is r. So if theta is very, very small, here it will be r cos theta plus d cos theta. So I can assume this is d cos theta and r cos theta. This is the theta here, and both the angles need not be same. Let me put theta 1 and theta 2. So d cos theta 2 and r cos theta 1. So this will be r cos theta 1. Again, theta 1 and theta 2 are just variables I defined right now. Both of them are going to be really, really small. So I can simply approximate the sum of the two. It's actually d cos of theta 2, where theta 2 is this angle, theta 2, and this is theta 1 plus r cos theta 1. But since we made this assumption that d is much greater than r, we can assume that theta 1 and theta 2 will be very, very close to 0. So then this number will simply be d plus r. So that's how we get d plus r here. Okay. Now the remaining things, which is d minus and d, this is a little bit involved but not difficult. So if you want to find this distance, okay, so we are supposed to find the one shown here in dotted blue. So again, I'll make some approximation. So this is theta here. If I project this directly onto this line, so till this distance, so from here to here, I can approximate this to be d cos theta. So theta is this angle here, cos theta. Now to find this distance, what I'll do is, this is r here, and this angle I'll approximate it to 60 degrees. This is within a cell. This angle is actually within the cell itself. As you can see, this cell is farther away, this angle is within the cell. See, the previous problem theta was very small, even though it is within the cell, but that's because of purely because of the distance where we are measuring, okay, purely because of the position of the other cell. So here I can approximate, see, ideally this entire angle is 60 degrees, okay, it has to be entirely, this is 60 degrees, but now I'm going to make an approximation that it's very close to 60. So this theta is 60. So if I project r here, you will get r cos theta, you will get r by 2. Cos 60 is half. So you will get d plus r by 2. D cos theta, which is theta here, is very close to 0 degrees. In this case, it is close to 60 degrees here. Okay. So you get r by 2, d plus r by 2. Okay. Now finally, to find the distance here to here, so this is going to be, see, these are approximate results. You'll have to digest these approximations that we are making now. Now to find the projection for this guy, I'll project it on like this, and this is the actual projection for this, so this distance, this whole distance is going to be d. If I put d cos theta, again theta is very, very small, so I'll assume it is d itself. Now I need to find what is this distance. What is this distance? Again, I'm going to make another approximation, so I'll have to zoom in that region to show you. So this was the center of the cell. This was the center of the cell, and we projected it this way. Okay, and this was the distance. Now you're supposed to find what is this distance. Now if you see, this actually is r by 2, and again that can be very closely approximated. This angle is very small, so this can be approximated to r by 2. So this whole distance is d, so that is from here to here it is d, and if you subtract r by 2 from this, you get d minus r by 2 here. So this distance will be d minus r by 2. So that's how you get that. Okay, so these are simple approximations. I just wanted to explain it once. So then once you know all the distances, then how do you compute? So assuming all the base stations, even the main base station transmits with power pt, every base station is transmitting with power pt, so it will be alpha times pt upon r power n. So I can write it as pt into r power minus n. That's your alpha into pt is a constant. That's your transmit power of the desired base station, divided by all the individual base stations. So you have 2 d minus r, so 2 d minus r power n minus n, d minus power n, which is due to this, and d plus r by 2. There is also a term d minus r by 2 whole power minus n, which is missing here. Okay, d minus r by 2 the whole power minus n. So that will be your total carrier to interference ratio due to tier 1 interferers. Now to further simplify this result, I am going to make another approximation that d is so great compared to r that you can neglect r. See, this will not be accurate. For example, if I choose n equal to 7, maybe you may not get accurate results. Okay, so if I see d by r is actually root of 3 and it is root of 21, you can make that approximation when n is greater than 10 or 20, okay, 20 or so. If your n is really, really large, then we can make it, but you may not get accurate results with this. So you may have to use this exact expression for smaller values of n. N is cluster size, capital N. Okay, that's what I'm talking about. Now, if you make an assumption for large values of n, where 20 or higher, okay, in that case it's going to be root of 3 into 20 or 3 into 25 or 3 into 20, it will be root 60. Okay, so d by r will be really, really large, so in those cases, I mean, in fact, even larger values of n. So in that case, I can ignore r altogether. In fact, all these r's will be much smaller compared to d, so I can assume every distance is d itself. So you will get a more simplified expression. You will get r power minus n divided by 6 times d power minus n. So finally the result carrier to interference ratio reduces to d by r whole power n into 1 by 6. So if you recall previously, when we assumed just one interferer, we got an expression of this form. There was no 6, the factor 6 was missing. Okay, now the factor 6 is there because of considering all the 6 tier 1 interferers. So you get 1/6 of, see, previously it was root of 3n whole power, I think minus 1. So 3n minus 1 the whole power n. Okay, so now there is an additional factor of 6. So if I can ignore 1, if n is really large, so then it will be root of 3n whole power n. Now if I assume 6 interferers, I am going to get 1 by 6. Okay, interferer power has increased by 6 times. So carrier to interference ratio will go down by 6 times. Okay, so that's how you get this expression. Now you have a neat relationship between carrier to interference ratio and the cluster size n. Of course, once path loss is fixed, so this is something we can't tamper with. So this is entirely what the reality gives us. Okay, we have to live with that. But cluster size is something we can fix. So we'll see if this cluster size is going to give us the desired carrier to interference or not. Okay. So based on user capacity, cluster size also gets decided based on the user capacity. And yeah, so what is that's again a decision an operator has to make. And what is the transmit power he is ready to shell, how many base stations he is ready to build. Okay, so your cell radius is determined also by that. Okay, your cell radius is determined by the operator. So based on what is the transmit power, what is the expenditure is ready to, how many base stations is ready to install in a given region. Okay, cell radius gets decided based on that. Okay. Now finally, now we are done with the analysis of carrier to interference ratio, a more accurate analysis, and related it to the cluster size. So now as a finale to all this, so we'll just relate what we want. Eventually what is our goal is the user capacity. You have to serve as many users as you want with a good quality. Okay, with a good quality communication, you need to support as many users as possible. So that's the whole goal. So we'll derive some simple results between user capacity and carrier to interference ratio. Okay, so carrier to interference ratio and user capacity are very important terms which determine your performance of a cellular system. So first, any given region, in all the analysis I'm going to assume your cell radius is fixed. Okay, if you fix the cell radius, then any area can be filled out using a fixed number of hexagons. Okay, and I'm calling those fixed number of hexagons as L. Once you fix the cell radius, the number of hexagons you need to fill out in a given area is fixed. I'm calling that as capital L. So that capital L is nothing but, if you know the cluster size n, so that will be n cells in one cluster, and you have m such clusters. So total number of cells will be m into n. So L is equal to m into n. Now we also know the user capacity, the number of users you can support, simultaneous users you can support in a system is S into M, right? S is the number of channels, and this S is being distributed among n channels. And you have those S channels repeated m number of times, reused m number of times. So the total number of simultaneous users you can support is S into M. Now I'm going to rewrite m in terms of L and n, so that will be S into L by n. So now if you see, your user capacity is inversely proportional to the cluster size. It's just a direct inverse relationship between user capacity and cluster size, and that should make sense, because if you increase your cluster size, then the frequency reuse actually is coming down. You're reusing your frequency less number of times. Okay, m reduces, you're going to use your cluster, you reuse the frequency less number of times, so therefore we lose out on the number of users you can support. The more times we reuse it, the more number of users we can support. But when we use more times, your carrier to interference ratio will increase. So that's what I'm trying to come at here. Okay, a reduced N means less frequency reuse. M is an indicator of number of clusters, means number of times you can reuse the frequency, which in turn leads to a higher user capacity. If your user capacity, if your N reduces, which means I need to reuse, I need to fill out the area with more number of clusters, which means user capacity is increasing. Okay, I'm reusing the same frequency for many people. Now we are also aware that the carrier to interference ratio is proportional to the cluster size N. Okay, so we know that if you increase the cluster size, carrier to interference ratio is definitely going to increase, but user capacity will reduce. And if you reduce the cluster size, carrier to interference ratio will reduce. Okay, now we will try to relate the user capacity and carrier to interference ratio. So the only parameter that's relating them is N. Both, see, S and L are constants here. Once you fix the number of channels and number of cells, radius is fixed, L is fixed. The only variable here is the cluster size N. Similarly, in the carrier to interference expression, the only variable here is the cluster size. But they both are inversely related to each other. Okay, so if you increase N, CIR increases, carrier to interference ratio increases, but the user capacity reduces. So I've assumed alpha and beta as two constants and expressed user capacity and carrier to interference ratio purely in terms of N. Okay, so then I can have a relationship between carrier to interference ratio and user capacity in this way. If you just rearrange the terms, N, if you see the cluster size N is inversely proportional to the user capacity. So if I substitute this in this equation, I'm going to get 1 by C user into N power N by 2. Okay, that's what I'm going to get. So which means if I want to increase, if this is again, the assumption here is cell radius is fixed. So the number of total cells in a given region is fixed. If I want to increase the number of users, then I have to take a hit on carrier to interference ratio. There is other way of increasing cell user capacity as well. I can simply shrink the cell size. In that case, I'll need more cells to fill out the area. So which means I'm increasing L itself. Okay, I'm increasing L itself. Or you can say M also, because now I'm going to need more clusters to fill out the area. Right? The cluster size is fixed. The N is fixed. I'm keeping N fixed, but I'm reducing the cell radius. If I reduce the cell radius, the smaller cells become smaller in size. So now you need more cells to fill out the area. Okay, then I'll need the value of M, user capacity goes high, and C, carrier to interference ratio remains the same because your N is fixed, cluster size is fixed. Okay, but user capacity is increasing because the number of cells itself are increasing. So that is the other way of doing it. Again, that's a cost expenditure. You'll have to expend more now because you will need more base stations, more infrastructure money. Okay. So that's it about carrier to interference. So now we will quickly talk about, so again, this is something, a question one of the students had asked doubts about, a question on can we use CDMA between cells. I've explained that in the class. I've written the explanation here. So I think this is really not necessary for this lecture, so I'll leave it out. You can read the slides. If you have any doubt, you can get back to me on this one about the idea of TDMA between cells. So I'll ignore that right now. Now, because I'm trying to reach, so this is again a very important problem. We'll talk about channel assignment strategies. How do you assign channels in the given cells? So we said once you know the cluster size N, you have S number of channels. We said each cell in a cluster is going to be uniformly given K channels, where K equals S by N. But in reality, maybe it might turn out that some cells have higher population compared to the other cells. The users are much higher. Maybe in a region like a hostel and let's say residential complex versus a hostel, there are more students. Maybe if every student has a cell phone, there is more users in that area. Okay, so in that case, this falls under the umbrella of what we call as static channel assignment, meaning once I assign the channel, I'm never going to change it. Okay, so those are called static channel assignments strategies. Now, in a static channel assignment, there is one first way, the obvious way is to give equal number of channels to all the cells. So this is a non-discriminative blind assignment of channels. Okay. The other way is to actually give those channels where the users are more, we'll give those cells where the users are more, we'll give more channels to those cells. Where the users are less, I'm going to give them less channels. So again, there I'm going to give variable channels to each cell. But we know this, the sum of all the channels is equal to S. That condition has to be satisfied. That is obviously satisfied. Okay. Now, there are two ways in which we can assign the channels. This is a static channel assignment wherein we don't change the channels at any time. For as a function of time, they are fixed forever. But this is obviously not efficient because most of the times cellular systems are by default designed for mobility. So meaning I have designed it for a certain number of users U1 in this cell and for U5 in this cell, but maybe there is an event happening in say cell 5, most of the users are going to switch to this region. Okay, if that happens, then a fixed channel assignment is always inefficient. Again, the users can again come back to this region, maybe even U5 users, more users may be coming to this region cell 1, maybe some event is happening in cell 1 and you have more users in that region. So in those cases, assigning a static channel assignment is not an optimal solution. So in that case, what we do is we do what we call as dynamic channel assignment. So we will vary dynamically, the channels will keep varying per channel. Now what you do is you don't assign any channels to any of the cells here. All the cells will be assigned no channels in the beginning, at first. Then what you do is, so there is something called, every cell will have a base station. Now all these base stations are connected. There is a backbone network called mobile switching network, MSN. They are all connected to an MSN. Now when a phone call, when a base station, when a cell phone is making a call, an MSN gets a record. Okay, now it knows that, okay, this is within the base station, so you take care of it. It tells this base station to take care of it. Okay, we'll later discuss something called handoff, and that is also, the decisions will be made based on by the MSN. There is a switching circuit which will actually a network which will actually take care of all the handover. We'll discuss what is handover later between two cells and all that. So this channel assignment is actually done by a more of an intelligence unit. You can call it as an intelligence unit. This is a mobile switching network will do that for you. So first, no channels are assigned to any of the cells. Now first, let's say there are more users in one particular cell trying to make a phone call. So then this MSN will assign more channel to this cells and less channels to other cells. If there is only one phone call in one cell, it will assign one channel. In cells, let's say this cell has no phone call at all, then the MSN won't assign any channel at all. So previously in a static channel assignment, all the cells were getting wasted, right? We had assigned K7 number of cells to this cell, K7 number of channels to this cell. But since nobody was making a phone call there, those channels were simply unused. And the other cells were underused because the other cells were overused because all the channels were used. Let's say in K5 many users were there, then a lot of fifth cell, a lot of users were using it and they were not getting enough calls because there were not enough channels. Okay, but now what we can do, because of dynamic channel allotment, nobody is using, I'm not going to allot any channel to K7. Instead, all the channels I have allotted to K7 previously can be allotted to K5. I mean, all the K7 channels can be allotted to cell 5. Okay, so this way I can increase the user capacity. So by dynamic channel assignment is obviously superior to a static channel assignment. Okay, so this is done by a backbone MSN, mobile switching network, where all your base stations are connected to that. So that MSN will know each base station has an ID. So that's called a cell ID. So each base station has its own ID, and MSN will know the base station by its ID. Okay, so then it will accordingly say which base station should get which channels and all that. So that's called a dynamic channel assignment. That will always be better compared to a static channel assignment. And see, every channel is a resource. Okay, now the base station has to do all the computations. It has to keep track of, in case of a dynamic channel assignment, the mobile switching network has to keep track of all the channels. It has to do a lot of processing there. Of course, the processing work is now transferred to the MSN. See, previously when we do static channel assignment, there is no processing necessary. Right? You don't have to find which cell has more and then accordingly change the cell channels number of channels dynamically. You don't have to do that, but now you have to do all that if you have a dynamic channel assignment using all that mathematics. The computations will be done by an MSN, the mobile switching network. Okay. So this again, I'll come back to this term called user capacity in a cell. So generally, let's say we use FDMA system with k channels per cell. I can generally support k users per cell. I can at max support k user per cells simultaneously. Okay, but later when we go to trunking and grade of service, we will see that the number of channels will usually be much lower than the number of users in a cell, and still it works. So how does it work? So that we'll do that analysis later. Okay. Now, I mean, the main point why I was talking about user capacity here is that if you have a static channel assignment, any cell can have at max an access to k number of channels. If I go for a fixed channel assignment where every cell gets equal channels, if each cell has k channels, you can support simultaneously k users. In case of a dynamic channel assignment, if let's say no other cell is using any channels, but only one cell is trying to make all the best of it, meaning all the users in one cell are trying to make calls, then an MSN can assign all the S channels to that one cell itself. So now each cell can have a capacity of k S. Yes, it can support S users simultaneously. A single cell itself can support S users, and that's really a high number compared to a fixed channel assignment. It's a very small comparison, but we'll actually properly do an analysis when we go to trunking and grade of service. Now that we spoke about interference, we should also discuss about techniques to mitigate interference. I think I discussed this very briefly in the lecture. How do we mitigate interference? So one classic technique which is called as sectoring. So what we do is we actually sectorization, instead of having an antenna, one single antenna radiating along all 360 degrees, the base station will now have 3 sets of antennas. One set of antenna will radiate in 120 degrees, and another 120, and another 120, and so on. Okay. So now what I'm going to do is that I initially had k number of frequency channels. I'm going to divide those into k by p, where p is the number of sectors. In this case, I've shown an example 3. So each sector will be given k by 3 number of channels. So I'll have k by 3 here, k by 3 here, and k by 3 number of channels. So I'm going to reduce the number of channels per sector. Okay, because the area of coverage is less. I'm assuming users are uniformly distributed, so I can reduce the number of channels per cell. But now they are going to radiate in a sector instead of radiating all 360 degrees. Now I've shown here graphically how that helps us here. Okay, so I have considered a mobile user at the edge of a cell. Okay, at the edge of a cell. So when he is standing at the edge of the cell, I have actually shown the radiation region, the radiation zones for the 3 interfering antennas. So the cells which will affect us. So let's assume that this is using F1, this region is also using F1. So this region will be using F1 frequency. This is using F1 here and F1 here. And this is F1, F1, and F1. So now if you see, these 3 base stations are not going to interfere with my, they are not going to generate interference because they are going to radiate in the other direction. Okay. So the ones which are going to cause radiation to me, or the interfering radiation to me, to the user here in the first base station, which we are interested in, okay, will be only 3. It's reduced nearly by half. In fact, if I have considered a cell edge here. That's why I'm getting radiation from this, interference from this guy as well. If I consider any other point within the cell, I'll have only 2 interferers. So this guy and this guy will only contribute it. Okay, but since we go for a worst case design in cellular systems, so I've considered an edge here where there will be 3 such interferers. So I can go for further smaller sectors. If I ensure the radiation is even further reduced by a smaller sector, so then we can actually show that it will be just only 1. You can even reduce it just to 1. If let's say I reduce the angle of radiation for each guy, okay, so then it can be that only this guy, the one which is immediately behind that, will actually contribute to all the radiation, the interfering radiations. Okay, so by sectoring we can solve the problem of, we can reduce by a good amount. So for example, if I said, if I go for a 60 degree, if let's say I had gone for a 120 degree sectorization, in this example directly, if you see, instead of having 1 by 6 root of 3n whole power n, this is the carrier interference ratio, as for tier 1 interferers. Now this is going to be slightly reduced. This is going to be 1 by 3 root of 3n. So I have reduced the carrier to interference ratio by 3 dB. I have increased the carrier to interference ratio by 3 decibels. Okay. Now if I assume if your cell phone is anywhere other than the edges, in fact your carrier to interference ratio will actually go up by 5 dB, because it will be 3, it will be 2, 1 by 2, there will be only 2 interferers. So you will gain by 10 log of 3, I think is 4.7, so around 4 to 5 dB. So that's how you get an improvement in carrier to interference ratio. Okay. So sectoring is obviously one technique, but the disadvantage of sectoring is that now, because we have divided frequencies within the region, see, whenever you design a cellular system, you always design it keeping mobility in mind. You have to ensure that users can keep moving in the cell and still you can have no call drops. But now, because the channels, I have to change when a cell phone is going to move from one sector to the other sector, it's going to a different base station antenna itself. The base station is same, but the antenna is different. So a new antenna has to radiate to this, and it will change the frequency channels also. It can't use the same carrier frequency as it was using here. Okay. So then there will be a probability of a call drop. So that is one problem. Okay. Now within a cell, we are going to have lower user capacity. So again, the same problems persist. If let's say I've given only fewer channels in a given region, this base station, if most of the users are in this region, then I'm going to have problems with supporting all the users simultaneously. Okay. Now there are further other techniques of reducing even further interference even further, and that is, like we said, if F1 is if instead of doing a fixed channel assignment, I can actually do frequency hopping. I can keep hopping the channels. I have shown here. So I have actually changed the channel assignment randomly. By doing this, on an average, I can reduce the interference seen by the main base station. Okay. So sectoring, you just have to know that sectoring helps in reducing the base station interference. So this is one such technique. And of course, cluster size obviously will be the other technique as well. So these are techniques which are used mainly for reducing interference. If I reduce interference, cellular systems are mostly interference limited. So if you reduce your cellular interference, then you can have a better quality. Okay. When I say quality, B or bit rate will be really low. So that's what I mean by a better quality. Okay. So with this, we have discussed main important points of cell splitting and frequency reuse. The main problem of frequency reuse and cell splitting is, to accommodate more and more number of users, we went ahead with the idea of frequency reuse. Okay. But the problem of frequency reuse is that it introduced interference. So there is a big problem of interference. Now we discussed how to quantify interference, and we also very briefly discussed what are the techniques of solving interference, resolving the problem of interference. Okay. So that's what we discussed so far. Now the most important aspect in a cellular communication is mobility. How are we going to ensure when a cell phone is going to go from one cell to the other cell that a call is still ensured without blocking? Because the other cell uses a different frequency altogether. So how is this, how do we actually deal with that problem? So problem of mobility. So that's the main thing which distinguishes cellular phone from every other wireless standard. That is, it can give mobility. Okay. Even moving vehicles can have access. When you are moving from one cell to the other cell, also you can still have a call without any blocking. Okay. So that we will be discussing in the next lecture.